Okay, so in this video we're going to find the magnetic field around infinity straight current carrying wire. So let's say you have this wire here, that carries a current I. So you want to find the magnetic field at any point around it, So the first question is like, which law are you going to use to do that? So we're going to use what is called the Ampere's law. We're using the Ampere's law to find the current, the magnetic field around the straight wire. So the reason we're assuming that it's infinity is because we know that at endpoints this will produce a non-uniform magnetic field, but at any point that's far away from the infinity point, we're going to have a uniform magnetic field. By saying it's uniform, it's like it's going like this, in a circular form everywhere. So how to do that? We're going to use what's called the Ampere's path. So we're going to draw the Ampere's path around this wire. So how to draw the Ampere's path? Ampere's path is the perfect circle that's symmetric. So this thing has to be symmetry. So meaning that this and that, they have to have the same radius from the center of the wire. So if they have the same radius from the center of the wire, we are going to say the magnetic field at this point, magnetic field B at this point, is the same as magnetic field B at this point. So how to find that magnetic field at that point? So using the Ampere's law says that the integration of the magnetic field multiplied by the length, the length of the Ampere's path is equals to the mu naught multiplied by the closed current in the Ampere's path. So the Ampere's path is from this point here, let's call this point A, going like that, going like that, going like this, going like it's like going like this, going like this, going like this, coming back here. So it's Ampere's path. So magnetic field at that point, since these two things are parallel, because when you say dl, actually you are taking the small point here, actually it's the tangent to this path. So the tangent to this path, while also the magnetic field at this point here is going this way. So both of them are going into the same direction. So by taking the cos of 0, you will get 1. Therefore is the same as B multiplied by dl is equals to mu naught. The current that is enclosed by this path here enclosed the current I, because I said the current in this wire is I, so it's just I. After that, what are you going to do? You're going to say, therefore this B is it's constant. You take it out, then you're left with dl is equals to I mu naught I. So dl is the distance from here, from point A, as I told you, going like this and come back. So that's like it's a displacement of the circle. So the integration of dl is equals to the displacement of the circle. Displacement of circle is a displacement of circle. So what's the displacement of circle, guys? You know that there's a 2 pi r, which is equals to mu naught I. So what's the B? Magnetic field at any point of infinity carrying current wire is equals to mu naught I divided by 2 pi r. Okay, thanks for watching.